KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss about angular momentum in case of rotation about a fixed axis. Okay, see here ma. So regarding this angular momentum, we already discussed. Okay, we already discussed that. You know the time rate of total angular momentum of a system of particles about a point is equal to the total external torque, okay, which is total external torque on the system taken about the same point. Okay, I will repeat once again ma, you please concentrate. Why? Because in this class we are going to discuss about angular momentum in case of rotation about a fixed axis. But regarding this angular momentum, already in our previous classes we discussed. What I am saying is, what we discussed about this angular momentum in our previous classes means the time rate of total angular momentum of a system of particles about a point is equal to the total external torque on the system taken about the same point. That is what mathematically I can say simple. That is what tau is equal to dl by dt. Tau is equal to dl by dt. Okay, right. Here itself I can say some more extension, that is when the total external torque is 0, the total angular momentum of the system is conserved. Okay, that is here itself again I want to say tau is equal to dl by dt. Tau is equal to dl by dt. Okay, right. Now this is what we are going to discuss in this class is like a special case of rotation about a fixed axis. It is studying of angular momentum about a special case of rotation, around or about a fixed axis. Okay, right. The general expression for the total angular momentum of the system is given is, that is L is equal to, it is a vector quantity, it is also vector, see L is equal to sigma I is equal to 1 to n Ri cross Pi. It is a position vector, it is a momentum vector. Okay, so this is the expression when we extended for n number of particles from I is equal to 1 to I is equal to n, then we are getting the total angular momentum of the system as L is equal to sigma I is equal to 1 to n Ri bar cross Pi bar. Okay, right. This is what the figure which shows the rotational motion of a single particle about a fixed axis. This is what fixed axis, and it is the direction of angular velocity in which the body is in rotation, and afterwards it is the linear velocity, the tangential circle, the tangent to the circular path, and it is the point P, right? And this is what C, it is Cp, and it is Co, and this is R, but this is the perpendicular distance. This is the distance of a particle from this point, but this is the perpendicular distance. So Cp is the perpendicular distance. Okay, right. So this picture is important for us to discuss the angular momentum in case of rotation about a fixed axis. Okay, see here ma. we first consider the angular momentum of a typical particle of the rotating rigid body. A typical particle. So, for example, first we are going to consider a particle to discuss angular momentum. Okay. We then sum up the contributions. Of the individual particles to get angular momentum of the whole body. Okay. So, first we are going to take for a typical particle. After that, we are going to add up. To get the angular momentum of the whole body. See here, for a typical particle, angular momentum L bar is equal to R bar cross P bar. Okay, see this. From the figure, this is what you can say, R is equal to OP, that is equal to OC plus CP, with P is equal to MV. P is the linear momentum. Linear momentum is also vector quantity, but mass is a scalar quantity and velocity is also a vector quantity. Now, you can also write based on this and this, you can also write L bar is equal to OC bar cross MV bar plus CP bar cross MV bar. Okay, OC bar cross MV bar plus CP bar cross MV bar. Here, the magnitude of the linear velocity V bar of the particle at P. The magnitude of the linear velocity. V bar of the particle at P is given by V is equal to omega into R perpendicular. That is what V is equal to omega into perpendicular distance, where R bar is the length of CP. This is the CP, amma. This is not R bar, it is R perpendicular. R perpendicular is the length of CP. R, the perpendicular distance of P from the axis of rotation. The perpendicular distance of P from the axis of rotation. Okay, right, full stop. Further, V bar is, this is what V bar? V bar is tangential at P to the circle which the particle describes. V bar is a tangential at P to the circle which the particle describes. Okay. Using the right hand rule, one can check that CP bar cross V bar is parallel to the fixed axis. CP bar cross V bar means there is a resultant vector, no? If you get the cross product of these two, you will get another vector. That vector is parallel to this axis. That he is saying. Please try to understand. That is the purpose of right hand rule here. Now, the unit vector along the fixed axis is k cap. Okay. So, this is what fixed axis means, chosen as the z axis in our picture. Okay. Hence, what can we write? CP bar cross MV bar is equal to R perpendicular into MV into k cap. That is equal to M into R perpendicular whole square omega into k cap. V is there, no ma? In place of V, we are writing this one. That is what see here, omega into R perpendicular. Already R perpendicular is here. Okay. So, it is what M into R perpendicular whole square into omega into k cap. Since V is equal to omega into R perpendicular. Right. Now, similarly, we can check that OC bar cross V bar is perpendicular to the fixed axis. Right. Let us denote the part of angular momentum. Along the fixed axis, that is z axis. Okay, by Iz. Then what will happen? Iz is equal to Cp bar cross Mv bar, that is equal to Mr perpendicular whole square, Mr perpendicular square omega into k cap, and L is equal to angular momentum, L bar is equal to angular momentum about z axis, L z bar plus OC bar into MV bar, right? OC bar into means here this is what cross product. That symbol you know, what is the notation to represent cross product? You know, right? That is OC bar cross MV bar. So it is what IZ, it is what angular momentum. Angular momentum L bar is equal to LZ plus OC bar cross MV bar. Okay, right. Here IZ is parallel to the fixed axis, but L bar is not. That is the important point you have to keep in mind, because you know very well, when we talk about one particular physical quantity, if it is a vector, we must be very careful about the direction, because if direction changes, the meaning will change, That's why here in this class the total discussion is about angular momentum, okay? And basically momentum is a vector quantity. In this discussion, in the middle of the discussion, we are getting so many vector quantities. For example, right here, that is what linear momentum is a vector quantity, and position vector is also vector quantity, and velocity is also vector quantity. That's why we must be very careful about the quantities when it is a vector. When it is a scalar, no problem, because it has only magnitude. Okay, right. So observe here, IZ is parallel to the fixed axis, but L bar is not. Now see here, in general, for a particle, the angular momentum L bar is not along the axis of rotation. In general, for a particle, the angular momentum L bar is not along the axis of rotation. Okay, that is for a particle, angular momentum and angular velocity. That is for a particle, angular momentum and angular velocity are not necessarily parallel. Okay, full stop. Compare this with the corresponding fact. In translation. That is what translational motion. Okay, and for a particle P and V, P bar and V bar are always parallel to each other. Now, if you observe carefully, for calculating the total angular momentum of the whole rigid body, we have to add up the contributions of each particle of the body. Then you can write mathematically, for whole rigid body you can write like this: L is equal to sigma, it is what Li, that is equal to sigma in place of, that is what Liz plus sigma, this is ma. So this we are writing here. Okay, it is just in place of Lz we put, this is for ith particle, it is general expression, but it is for ith particle. Okay, the same thing, whatever is here also the same thing. Okay, now this is what L perpendicular and Lz. Okay, L perpendicular and Lz. Here, see here, for a whole rigid body, this is the expression for ith particle based on this. And now this L perpendicular and Lz, this is what L perpendicular, right, and this is what Lz. Okay, this L perpendicular and Lz are the components of L, respectively perpendicular to the z axis and along the z axis. I didn't write here, but I am saying. So this is what Lz and this is what L perpendicular. These are the components of L. So one is perpendicular to the z axis, another one is parallel to the z axis. So parallel to means what? Along the z axis. Okay, right. Now you can write this one, L perpendicular is equal to sigma OCI bar, because it is a vector, into, that is what cross product, into means here cross product MIVI bar, this is one, and Lz is equal to sigma Liz, that is equal to sigma I mi square, sigma I mi square into omega into k cap, omega into k cap, okay, or Lz is equal to I omega into k cap, Lz bar is equal to I omega into k cap, okay, right. Now the last step, so whatever the last step, right, whatever the last step, here the last step follows, the last step, this is what follows, since the perpendicular distance of the ith particle from the axis is r1, okay, the last step follows since the perpendicular distance of the ith particle from the axis is r1, but here we are taking ith particle, no, so that's we have to take ri, not r1, so this is what ri it is not 1, it is I. So the perpendicular distance of the ith particle from the axis is ri, and by definition the moment of inertia of the body about the axis of rotation, that's that is I is equal to mr square, but the complete expression means I is equal to sigma mi square, okay, right. Note L bar is equal to Lz plus L perpendicular, L bar is equal to Lz plus L perpendicular, okay, right. Now the rigid bodies, here I want to say some information, you just be concentrate. The rigid bodies which we have already considered from the same chapter generally are symmetric about the axis of rotation, So what does this mean? This means that the axis of rotation is one of their symmetric axis. The axis of rotation is one of their symmetry axis, okay, right, full stop. For such bodies, for a given value of OCI, for such bodies, for a given OCI, for every particle which has a velocity Vi, there is another particle of velocity minus Vi located diametrically opposite on the circle with the center Ci described by the particle. So you please try to understand the situation, okay. For such bodies mean what? For symmetric axis, right. In case of rigid bodies, regarding the symmetry, for such bodies, for given OCI, for every particle which has a velocity Vi, there is another particle of velocity minus Vi located diametrically opposite on the circle with center Ci described by the particle, okay. We can write, so here itself we can write L bar is equal to Lz bar is equal to I omega into k cap, okay, right. For bodies which are not symmetric, about the axis of rotation, observe carefully, for bodies which are not symmetric, about the axis, see here. So this is what I told, it is for the same particle which is diametrically opposite on the circle with center Ci described, okay. Now described by the particle, okay, right. Now we can write this one. So how can we write this one? Because such pair, one side one particle, diametrically opposite another particle, together such pairs will contribute 0 to L perpendicular, and as a result for symmetric bodies L perpendicular is 0, and hence when L perpendicular 0, only Lz is available, no. So then total angular momentum L bar is equal to Lz bar is equal to I omega into k cap, okay, right. Now for bodies which are not symmetric, you can write this one. For bodies which are not symmetric about the axis of rotation, angular momentum, total angular momentum L bar is not equal to Lz bar, and hence L does not lie along the axis of rotation. L does not lie along the axis of rotation. Okay. So certain information here I didn't write ma. You just listen what I am saying. For bodies which are not symmetric about the axis of rotation, L bar is not equal to Lz bar, and hence L bar does not lie along the axis of rotation. Okay. And I already given one table ma before 4 or 5 classes, right? So for a cylindrical body and for circular plate and for that is what spherical bodies, and if you change the axis of rotation, what are the values of moment of inertia, right? So the table I have given. Okay. So the table also important here to discuss. And one more what I am saying is, referring to the table, with respect to the table, you can also say that here, right? First the question is it possible to tell in which cases L is equal to Lz will not apply? So to answer that question, we have to differentiate. We have to differentiate the equation. Then finally this you can write d by dt of Lz. D by dt of Lz is equal to d by dt of I omega into k cap. Here this equation already we know, tau is equal to dl by dt. So what can we say here? Already we discussed this information, but once again I am recalling you. Only those components of the external torques which are along the axis of rotation, only those components of the external torques which are along the axis of rotation need not to be taken into account. Need not to be taken into account when we discuss rotation about a fixed axis. So what does this mean? This means you can take tau is equal to tau into k cap. See here ma. Tau is equal to tau into k cap, since L is equal to Lz bar plus L perpendicular, and the direction of Lz bar is fixed. Direction of Lz bar is fixed. It follows that for rotation about a fixed axis, dLz by dt is equal to tau into k, and dl perpendicular by dt is equal to 0. Now, thus, for rotation about a fixed axis, the component of angular momentum perpendicular to the fixed axis, is constant, as Lz is equal to I omega k, d by dt of I omega is equal to tau, and now suppose if moment of inertia is constant, so mathematically while differentiating, if one quantity is constant, that you can take it as out now. So d by dt of I omega is equal to I into d omega by dt, that is equal to I alpha, and we can also get tau is equal to I alpha, right? So when tau is equal to I alpha, this is what work energy root, no? This is the equation, right? We have already derived this equation using the work kinetic energy root. That is what work done is equal to the external work done, the work done by the force. So in case of rotational motion, the work done by the torque is equal to, that is what, change in rotational kinetic energy. Okay, that's what we can recall once again here, because here we had tau is equal to I alpha, and at the same time we also had, that is d by dt of I omega is equal to I into d omega by dt, that is equal to I alpha. Okay, right. In this class we concentrated to discuss angular momentum in case of rotation about a fixed axis. So discussion about angular momentum is not new for us, because already we discussed linear momentum, that is linear momentum in case of translatory motion, but angular momentum in case of rotational motion. Okay, right. And but there is a relation, that is what, L bar is equal to R bar cross B bar. L bar is equal to R bar cross P bar. Okay. So here in this class, our concentration is to discuss the angular momentum in a special case of rotational motion about a fixed axis, about a fixed axis. Okay, this is the general expression for the total angular momentum, and this is the situation, and here you can write this one, and if R is equal to OC plus CP and P is equal to MV, you can write this one. And after that, this is you already know, V is equal to R omega, V is equal to R omega. Okay, and step by step procedure you can write all these things. But if you come to this point here, we got the discussion about angular momentum, which is perpendicular to the axis of rotation and along the axis of rotation. Okay, in one case, in one situation or one instant of time, it is L bar is equal to, it is not particular to one particular case, but generally L bar is equal to L z bar plus L perpendicular, right? L perpendicular, L is equal to L z bar plus L perpendicular bar. So based on that axis of rotation and symmetrical bodies and asymmetrical bodies, here we have to think with respect to both of them. And then finally d by dt of Lz bar is equal to d by dt of I omega into k cap. And by seeing this video 2 times or 3 times, you please try to understand in what situation we are saying that dl perpendicular by dt is equal to 0, and here we concluded that L perpendicular is 0, that's why we are writing L bar is equal to Lz bar is equal to I omega into k. Okay, and finally you can say these 2 statements, and at last d by dt of I omega is equal to tau. And if I is constant, you can say, you can write this one mathematically, and finally you can get it as tau is equal to I alpha. Okay, right. So thank you, and we will continue the next continuation topic in the coming class. Thank you.